Okay, we are now going to talk about how to find volumes using an integral. So let's suppose that we sought the volume of some particular solid. So let's say this is some sort of three-dimensional object, and it has a horizontal width. And let's say at any particular horizontal location in this solid, we can call x. And the beginning of the solid is the x value a, and the right-hand end of the solid is the x value b. All right, and we wanted the volume of this solid. So the way we're going to approach a problem like this is by cutting a slice right where any given x value is, like a cross-section of the solid. So imagine slicing right through wherever the point x is with a knife. And we're going to give it a little bit of width. So it's almost like a sort of a slice of ham or something. Okay, now this width we're going to call dx, which basically just, again, means tiny little change in x, because the width is in the x dimension. Now, I've said in the past that an integral is just like an adding machine. Okay, and what I mean by that is to figure out the volume of, say, an interesting shape like this. So our job is to do all the work to figure out the volume for one slice, and then we just throw an integral sign in front, and what that's doing is adds up all the slices. So we'll just find the volume of the one slice. Okay, so what are we going to call the volume of one slice? Well, how about tiny amount of volume, or tiny change in volume? And what is that? Well, that would be this area, which depends on x, so we'll call that a of x. And that area is multiplied by this tiny width, dx, which means the tiny bit of volume is that area multiplied by that width. So now we're just going to use an integral to add up all of these tiny little slices of volume. And so we can conclude, therefore, that the volume of the solid is given by just v, which is the sum of all the dv's. In other words, the integral. And we know that dv is a of x dx, and x runs from a to b in this case. Now, this is a general process for finding the volume of a solid. What we are going to see immediately is how to apply this to find the volumes of a particular category of objects that are constructed by taking the functions that we know and love from calculus and rotating them around an axis. All right, so let's let f be a continuous function on the interval a to b. So we can imagine our f right there, just minding its own functionally business. And let's suppose that a is right here and b is right here. So we can imagine taking this particular region and rotating it around the x-axis, which would produce, in a sense, a solid. So if we imagined rotating this thing, we would get something like this. So there's our x-axis, but we've now rotated the function from a to b and ended up with this three-dimensional solid. Okay, so of course what we're after, this should be no surprise, is the volume of that solid. And what we're going to do is implement the principle that we just talked about a few minutes ago, which is to find the volume of this solid, we're going to cut a slice into the solid and find the area of that cross-section. We will multiply that area by a tiny, tiny differential width, which we can call dx. And then we will have the volume of that disk. And then we'll use an integral to add up sort of an infinite horizontal stack of those disks, and that will give us the volume of this entire solid. So how do we find the area of that cross-section? Well, the cross-section is a circle because this was a perfect rotation around an axis. So it's a matter of just finding the area of that circle. Well, in order to find the area of that circle, we're going to need the radius of that circle. The radius of that circle is actually just the function value. So let's call it capital R. And let's note that the radius is just f of x, the function value there. On the original graph, you can see that the radius would simply correspond to this particular measure right here. It's the radius of the rotation. So we can say that the area of the cross-section, we'll call it a of x. Well, that's pi times the radius of the rotation squared. And as we just saw, that would be pi times f of x squared. And therefore, the volume of the disk, which we're going to call dV, well, we know that that's a of x dx, and so we conclude that the volume of the solid, being the integral of the dVs, will just be the integral from a to b of a of x dx, but a of x is pi times f of x squared dx. Okay, so everything we just saw can be nicely summarized into a technique called volumes of revolution disk method. So the volume of a solid obtained by rotating a function r units from the axis of rotation is given by the following formula. There are actually two of them, depending on if you choose to integrate with respect to x or integrate with respect to y. And they're basically the same formula. So there's the dx version, and there's the dy version. And the key here is that in the dx version, r is a function of x, usually just f of x. And in the dy version, r is a function of y. Okay, very good. All right, for our first example, we're going to prove the formula for the volume of a sphere. You've probably encountered this formula at various times. Well, we're going to establish this using calculus. So how are we going to do that? Well, think about what mathematical function you would rotate in order to produce a sphere. Okay, and that would be a circle. So what we need is, to start out, we need the equation of a circle. And we know from trigonometry that that's x squared plus y squared equals r squared. It's a circle of radius r centered at the origin. All right, but this also breaches the vertical line test, so technically it's not a function. So let's solve for y and create a function. So we're going to get y squared is equal to r squared minus x squared, and therefore y is equal to plus or minus the square root of r squared minus x squared. And what we'll do is we'll just specifically choose either the plus or the minus, and it doesn't matter which one you choose, which will give either the top half or the bottom half of this circle, and that'll be our actual function. So let's actually just let y be the positive square root, which will be the top half of the circle. Again, we're going to rotate it around the x-axis, so that top half's all we need to rotate around, and when it rotates a complete revolution, it will generate the sphere. Okay, so this is the region in here that we're going to rotate about the x-axis. Okay, so we're going to set this up using the disk method. So we know that the volume is the integral from a to b of pi times the radius of the revolution squared dx. So we're going to need to know the bounds, and we're going to need to figure out what capital R is. Well, the bounds are simple enough. This is a circle of radius r, which means that's negative r right there, and that's positive r. So clearly our integral is going to run from negative r to positive r. And what's capital R? Well, capital R is the radius of our rotation. And we can see that if this is a sample rectangle, which will get rotated producing one disk, then capital R is just the height of that rectangle. And the height of that rectangle is the dimension y. It's the length y. In other words, it's the function radical r squared minus x squared. So our volume is given by negative little r to positive little r, pi times, and what's capital R? The dimension of y, it's this vertical length right here. That's being squared, and we're integrating with respect to x. Now, that particular step is pretty unnecessary. We could just go directly in saying, well, capital R is f of x, so that would be the function. Capital R is equal to little y, and little y is equal to that. Okay, now again, I want to just pause here and say, this is the setup of our problem. So if the problem had only said set up an integral, then this is where we would have stopped and said, there's our final answer. We've set up the integral. Okay, so this particular example is to find the actual volume formula, so we're going to have to solve this all the way down. So now we just work out this integral. Well, we're squaring a square root, so that cancels the square root. And we can either distribute the pi, giving us pi r squared minus pi x squared, or you can factor the pi completely out. Let's just do that. So this is pi, negative r to positive r of r squared minus x squared. Let's quickly notice something about this function. This function is an even function, which means it has symmetry about the y-axis. If you look at the graph, that means that instead of integrating from negative r to r, you could integrate from 0 to r and double your answer. And that's a nice property of even functions. So in other words, for any even function, negative a to positive a of f of x dx is equal to 2 times the integral from 0 to a of f of x dx. So we could take this guy and say that's equal to 2 pi times the integral from 0 to r of r squared minus x squared dx. And now we're ready to integrate. This will be 2 pi times the antiderivative of r squared. Now r squared is just a constant, and this antiderivative is with respect to x. So it's going to be x times that constant minus antiderivative of x squared, which is that. And x starts at 0 and x ends at r. So we're going to have 2 pi times, we'll plug r in for x, so that'll be r cubed minus 1/3 r cubed minus 2 pi times, now we'll plug 0 in for x, but we can see that's going to just zero everything out. So we have 2 pi times r cubed minus 1/3 r cubed is 2/3 r cubed. And that's 4/3 pi r cubed, which we know to be the volume of a sphere of radius r. So we are powerful. All right, let's start by sketching the region. So 2x equals y squared. Well, that's like x equal 1/2 y squared. So that's just a parabola going through the origin that's horizontally oriented. And then the line x equals 0 is the y-axis. And the line y equals 4 is a horizontal line. Let's just say it's right there. So the region that's bounded by those curves would be this piece right here. And we are instructed to rotate that region about the y-axis. So that would give a shape like this. And we want to know the volume of that thing. So because we're rotating around the y-axis, our disks are going to be horizontal, right? So look at a cross-section here. A cross-section will be like a horizontal disk, and it'll have a slight height of dy, right? Tiny amount of y. So our radius is this horizontal length. Okay, but we're going to, of course, use the disk method. So our volume is going to be the integral from c to d, because we're integrating with respect to y, of pi times the radius squared dy. So again, we just have to figure out what c and d are, and we need to determine what r is. Okay, well, if we look at our graph, we can see that c is probably 0, and we can see that d, the upper limit of our integral, is of course 4 because of the line y equals 4. So our integral is just going to run from 0 to 4. And our horizontal length here, which is the radius, is just that x coordinate, which is 1/2 y squared. So we can say that v is equal to the integral from 0 to 4 of pi x squared dy. But x is equal to 1/2 y squared. So this is in fact the integral from 0 to 4 of pi times 1/2 y squared, and that quantity itself is being squared, dy. Okay, so let's finish this guy. 0 to 4, pi times, let's square everything. So we get 1/4 y to the 4 dy. And this is equal to its antiderivative. So pi times 1/4 times y to the 4th becomes 1/5 y to the 5th, and the bounds start at 0 and they end at 4. So we'll just plug 4 in here. We get pi times 1/4 times 1/5 times 4 to the 5 minus everything with 0 plugged in, which actually will just come out to 0. So here, this 4 cancels with one of the 4s, so we get pi times 4 to the 4 over 5. 4 to the 4 is 2 to the 8, so computer scientists might know that that's 256 pi over 5. All right, what if the region were described by two curves? So to get a sense of what I'm talking about, let's sketch two curves here. So let's say we have a function here. Let's call it y equals f of x, and it's minding its own functionally business. And now we have like a lower curve. Let's call it y equals g of x, and it's minding its own functionally business. And we still have an a and a b, and these are x values. But now we have a region that's bounded above by f of x and bounded below by g of x. What we're doing here is we are rotating, say, about the x-axis. And that would produce a very interesting solid with kind of a hole in the middle of it, right? What we would get is just from the outer function, the f here, something like that. But then in the middle, we have g rotating, and we'd sort of end up with a solid, a little something like this. Okay, great. Well, what would a cross-section look like? So a cross-section of this guy would be like tracking what happens if we take one narrow rectangle here of width dx and rotated it about the x-axis. Now, let's get our axis of rotation drawn in the solid here. That rectangle would emerge as sort of a circle with another circle removed from it. So a cross-section of this solid would be like a disk with a disk removed. And that shape is, of course, called a washer. So just as we did before, what we're interested in is the volume of that washer, and then we'll just throw an integral in front of it to add up all the infinite number of little washers that line up to form the actual solid. So, okay, yay, what is the surface area of that washer? Well, it would be, if you think of it as the surface area of the entire outer disk minus the surface area of the inner disk. So there are now two radii involved. There's the outer radius, which I usually denote with a capital R, and there's an inner radius, which we can denote with a little r. Let's take a closer look at this washer. I'm going to expand the inner disk of the washer just so we can see the pieces a little bit more clearly. So this has a thickness of dx, very narrow, thin, infinitely thin washer. There's an outer radius of capital R, an inner radius of little r. So we can see that the cross-section area of the washer is just the outer disk area minus the inner disk area. Okay, we'll call that, say, A of x. And the outer disk area is pi capital R squared, and the inner disk area is pi lowercase r squared. And if we factor pi out, we can say that that's pi times capital R squared minus little r squared. So multiplying by dx will give us the differential volume, a tiny amount of the volume. So the volume of a washer is dV, which is pi times capital R squared minus little r squared times the width of the washer, which is dx. And those are the things that we're going to add up in order to find the volume of this type of solid. So that leads us to a slightly more flexible method for finding volumes, which is called the washer method. All right, and as before, there are two versions of this, depending on whether you are integrating with respect to x or integrating with respect to y. So for integrating with respect to x, we integrate from, say, a to b, pi times capital R squared minus little r squared dx, or from c to d, dy. So in this case, r and r are functions of x. And in this case, r and r are functions of y. Okay, and lastly, I just want to point out that the disk method is actually simply a special case of the washer method with little r equal to 0. So you can technically think of the disk method and the washer method as one and the same in that sense. This is just, the washer method just kind of tells a little bit more of the story, a little more flexible. Okay, cool, a volume problem. So let's sketch the curves. Hopefully you remember from pre-calculus that what we have here are a couple of parabolas. So x squared plus 2 is just the default regular vertically oriented parabola shifted up by 2 units. And 4 minus x squared is an upside down parabola that's been shifted up by 4 units. So we must be talking about this region right here, and it's being rotated about the x-axis. So you can try to imagine the solid that would emerge by completing this rotation. And we want to find the volume of that solid. So as we would if this were an area problem, probably the first thing we should do is try to locate these points of intersection. And we'll do that by equating the two curves. X squared plus 2 is equal to 4 minus x squared. So moving everything to one side, we have 2x squared minus 2 is equal to 0. And we can factor like that, showing us that x is equal to plus or minus 1 are those two bounds. So our integral will run from -1 to +1. You can also see that these are even functions, which means we could actually integrate just from 0 to 1 and rotate that guy around, which will give us half of the solid, but we'll just double our answer. All right, well, let's take a closer look at this region. So one slice is going to come through like this. We're integrating with respect to x, so it's a very narrow length in the x direction. And that's going to produce a washer when we rotate that dx piece around. And you can see that the capital R will be this whole radius here, which is the upper function, and little r will be the distance to the lower function from the axis of rotation. So We'll start by setting up the washer method. Now, even if you have all the pieces figured out, it's a really good test-taking strategy to just write down the formula like we just did before you start plugging things in. Because if you happen to make a mistake setting something up, at least your instructor, me, I can give you partial credit because I can see that you at least know the correct formula that you should be using. Okay, so we've decided that this is from -1 to +1 of pi times capital R. Well, what is our capital R? Well, capital R is just the upper function here. So that's going to be 4 minus x squared, and that's being squared, minus the lower function, which is x squared plus 2, and that's being squared. And there's our integral. And once again, if this were a setup only problem, that would be the best place to stop. Okay, we noted earlier that these were both even functions, so we can double our answer and integrate from 0 to 1 instead of -1 to 1. And let's also FOIL out all of this nonsense. So we have 16 minus 8x squared plus x to the 4th, and x to the 4th plus 4x squared plus 4. And let's combine like terms here. So 16 minus 4 is 12. Negative 8x squared minus 4x squared is minus 12x squared. And this x to the 4th cancels with negative x to the 4th. So we can factor another 12 out of this, giving us 24 pi times the integral from 0 to 1 of 1 minus x squared. Very nice. So I think we're ready to integrate this thing. 1 integrates to x, and then x squared to 1/3 x cubed. Our lower bound is 0, and our upper bound is 1. And when we plug 1 in, we get 1 minus 1/3. And how wonderful it is to plug 0 into stuff when it just kills everything. So that whole right chunk is going to be 0. So we just get 24 pi times 2/3, which would be, what, 16 pi? Okay, very good. Okay, as before, let's start by sketching these curves, see what we're working with. So y equals 9 minus x squared. Well, that is an upside down parabola, vertically shifted to have a y-intercept of 0, 9. And y equals 0 is just the x-axis. And we are given specific bounds to go from 0 to 3 on x values. So, all right, well, here's x equals 0, and this is x equals 3. And we know that that's right where the parabola comes in, because when we plug 3 into the equation, we get 9 minus 9, which is 0. So y value of 0 there. So we are talking specifically about this region here, and we are rotating at about the line x equal -2. Well, this is our first example where we're rotating about a line that doesn't necessarily coincide with an actual x or y axis. So the line x equals -2 is -2 units out, so that would be this vertical line here. So that's the line we're rotating around, and that would produce a solid that sort of looks something like that. Great. I've always wanted to know the volume of a thing like that, so today's our lucky day. All right. So since we're rotating around a vertical axis like this, and we want to use a washer method, we're going to be integrating with respect to y. So our slices are going to look like that, and when you take that horizontal rectangle and you enforce the revolution on it, you're going to get like a horizontal washer shape here. So we, of course, are going to need a capital R, which is this whole distance from the axis of rotation to the far end of the rectangle. And we're going to need a little r, which is from the axis of rotation to the lower end, or in this case, the left end of our rectangle. So on the washer itself here, little r would just be the radius of that little disk, and big R would be the radius of the big disk. And they're both read from the axis of rotation. Okay, well, let's set up our integral. So our volume is going to be, and we are integrating with respect to y, so let's put CD here. Pi times capital R squared minus little r squared dy, which means that c and d must be y values to correspond to the variable of integration, and big R and little r must be functions of y. So first, let's figure out c and d. Those are probably the easiest things to see. Those are y values here. So the lower bound is, of course, going to be 0. So we can see that little c is going to be 0. And the upper bound is this y value right here, which is 9. So our integral is going to run from 0 to 9. Okay, well, what's capital R going to be? Well, capital R is this fixed length here, which is 2 units, plus this variable length here, which we can think of as just a variable x dimension. So let's call for a moment capital R 2 plus x. And we ultimately need to write it in terms of y. So how is that x defined? Well, y is equal to 9 minus x squared. So therefore, x is equal to the square root of 9 minus y. So we can say that our capital R is 2 plus that x direction, which is given by that curve, the parabola, 9 minus y under a radical. So there's what our capital R is. Lowercase r is always the same, and it's always just the fixed length of 2. So therefore, our volume, which is c to d, and I'm just going to write the formula once again. It's always a good idea to write formulas, is the integral from 0 to 9 of pi times capital R squared. Now, capital R is 2 plus radical 9 minus y. That quantity is being squared, minus little r squared, which is just 2 being squared, dy. Again, if this were a setup-only problem, that would be where you should stop. So we can factor pi out of the integral. We have 0 to 9, and we certainly have our work cut out for us algebraically here. Foil out this. We got 4 plus 4 times radical 9 minus y plus the square of the square root, so that'll just be 9 minus y, and then minus 4 dy. A little bit of cancellation right there. So let's put the 9 minus y in its own integral. and we'll split the square root of 9 minus y into its own integral. And the reason why I suggest this is because this integral on the right is going to require a u substitution because it's a composite function here. We have the square root of stuff, and that needs to be dealt with properly. So let's quickly do that. Let's let u be 9 minus y. So du is the derivative of that, negative dy. So we have pi times the integral from 0 to 9, 9 minus y dy, plus 4 pi times the integral of the square root of u times negative du. And what are our bounds? Well, when y is equal to 0, u is equal to 9. And when y is equal to 9, u is equal to 0. Now, we could factor the negative out and go negative 4 pi 9 to 0 square root of u du and go on our merry way from that point. However, let's use one more property of integrals here, where if you multiply an integral by a negative, you get to switch the bounds of integration. And I think that's a good idea here, because not only is our integral naturally negative at the moment, but our bounds of integration are kind of in the wrong order, right? The lower bound is 9 and the upper bound is 0, and we usually want a smaller number as the lower bound and a bigger number as the upper bound. So we can kill two birds with one stone here by switching the order of integration. So we have pi times 0 to 9, 9 minus y dy. We're going to change the sign of the integral to a plus, and we're going to swap the order of integration to 0 to 9. And we'll write this as u to the 1/2 because we're about to integrate it. So here we use the property that the integral from a to b is equal to negative the integral from b to a. Okay, I think we're ready just to integrate everything. You could have integrated the left a long time ago, but we're doing it now. So we have 9y minus 1/2 y squared. And the antiderivative of u to the 1/2 is 2/3 u to the 3/2. Okay, so we'll plug 9 in and then 0 in. So plugging 9 in, we get 9 times 9, which is 81, minus 1/2 of 81, so that would be 81 over 2. And plugging 0 in, we know that's just going to give us 0. Very nice. Now let's plug 9 into this guy, and we're going to get 2/3 times 9 to the 3/2. So that would be like 3 cubed, which is 27. And again, plugging 0 into this one will also just give 0, which is very nice. So those guys disappear. An object minus half of that object is just half of that object. So this is 81 over 2 times pi. And we're adding, what we have is 4 18s, which is 72 pi. All right, so 144 and 81, that's 225 pi over 2. Super awesome. Okay, let's talk just a little bit more about setups for a moment. Let's suppose we had the same setup as last time. So we've got that parabola, and this is the region we're interested in. And last time, we rotated it about the line x equal -2. And so our capital R was this fixed length of 2 here, plus x. And of course, x was the square root of 9 minus y. So our capital R became 2 plus the square root of 9 minus y. And our little r was just a fixed length of 2 the whole time. So we had little r equal to 2. Okay, very good. We've had this conversation. But how would things have changed if the axis of rotation were, say, over on this side? Say this is like x equals 10 is safe. We'll go with 10. Now, as I've said, capital R and little r always read from the axis of rotation. So our capital R now will be this guy here, going from the axis of rotation to the far edge of the region. So there's our capital R. Okay, well, what would that be? Well, in this case, it's a fixed length of 10. It's just 10 all the way down. Well, what's our little r? Our little r is the radius, the distance from the axis of rotation to the near curve. Now remember, the function here is x equals square root of 9 minus y. So what is that little r? Well, if we know this distance here is, and we'll call it x, which is being determined by that equation, then we can see that little r is the entire length, which is 10, minus this length of x here. Okay, but since we're integrating with respect to y, we would have to write this in terms of y, so we'd go 10 minus square root of 9 minus y. So if this were the situation, then our volume setup, which would still be with respect to y, so they'd be bounded from 0 to 9, it would be capital R squared minus little r squared dy, and it would be, in this case, pi times capital R squared, which is 10 squared, or 100, minus little r, and little r is 10 minus rad 9 minus y, and that quantity is being squared, dy. So there's our setup. Okay, the setup is probably the most interesting and complicated part of this problem, right? Once you have it set up, it's just mechanics working out the integral from that point on. All right, so be very careful when you're setting up a washer problem where the axis of rotation doesn't necessarily coincide with the x or the y axis.